Tonight on Nova, the Mississippi gets a state-of-the-art bridge.
Nobody had ever done this before anywhere in the world.
Be on site as we dive and drag, pound and pour, around the clock, against the elements.
Lately, our luck's been running pretty sour.
You can't control the load. It's out of control.
Make way for the bridge of the future. A Nova 2-hour special, Super Bridge. Major funding for Nova is provided by the Park Foundation, dedicated to education and quality television, and by the Corporation for Public Broadcasting and viewers like you.
It's midsummer, and the river flows through the day in a dreamlike trance. The Indians called it Mississippi, the father of waters. To Mark Twain, it was a symbol of eternity. For centuries, the Mississippi has served as a great flowing highway for people and wildlife alike. Along its banks are hundreds of towns, like Alton, Illinois, that sprang up in the 19th century. After European settlers pushed out the local Indian tribes, they began to build and build. You can still find the old Alton almost everywhere you look, and the families who bought a piece of it. For them, the past is one of Alton's biggest attractions. But like so many old river towns, Alton has struggled to make ends meet. For many people here, the future counts more than the past. They know that whatever the guidebooks say, Alton doesn't live off the river trade anymore. And the river can be as much a barrier as a thoroughfare. A barrier that has to be crossed to keep the town alive. For nearly 70 years, the old Clark Bridge has been the most direct route from Alton to St. Louis, the commercial center of the region. But the bridge was built in the days of the Model A Ford. It carries 20,000 cars and trucks a day in just 2 lanes. It groans under the weight of its burden. It squeezes the flow of traffic without mercy until it slows to a crawl. And as the bridge ages and becomes less and less fit for the job it was meant to do, Alton begins to fear that its economic prospects are being squeezed as well. By the late 1980s, the town and the state governments of Illinois and Missouri are all in agreement. They and the river need a new bridge at Alton. Over the next 4 years, Joe Leach will supervise a team of specialists who will ensure the quality of the new bridge. A consulting engineer, Leach has been hired by Illinois to check every detail of construction. Nothing can be taken for granted. At stake will be Leach's reputation, his career, and most importantly, the public safety.
We have a contract with the Illinois Department of Transportation, but we have a bigger contract, and that contract is with all the taxpayers in the state of Illinois and the general public that will use this structure. Because when we walk away from here, we want the general public to believe, as they should rightfully so, This structure is sound. You can use it, and you can use it safely.
Every time a bridge crosses a river, it has to solve a unique set of problems in safety, aesthetics, and cost. Changes in technology have always led engineers to new designs, but it's never an easy choice. One possibility for Alton is a structure called a truss. It's extremely strong, but it uses so much structural steel that it's very expensive to build and maintain, like this 45-year-old St. Louis bridge. Another option is called a tied arch because the road deck ties the two ends of the arch together like the string of a bow. This is the Jefferson Barracks Bridge, also in St. Louis. But a tied arch requires the building of temporary supports in the river that would dangerously narrow the shipping channel during construction. A third possibility is a classic suspension bridge. But given its high cost, it only makes sense for extremely long spans like the Golden Gate Bridge in San Francisco. There is, however, a close relative of the suspension bridge that combines strength and relatively low cost. It's called a cable-stayed span, and some say it's the wave of the future.
The modern cable-stayed bridge started after World War II in Europe, in Germany primarily, and in some in France, but primarily Germany, because they had a number of their bridges had been destroyed during the war. Their steel mills had been destroyed. Even their concrete ability for materials were not there. The engineers had to develop a way in which they could design a bridge with the least amount of materials to span long distances and to be as economical as possible.
The designers of the new Clark Bridge begin with a single pair of towers which will support the whole main span. Ordinarily, the cable stays would be placed in a single plane like this. But the Illinois Transportation Department wants the road deck supported at both outside edges, not only for maximum stability, but also for minimum cost, because a well-supported deck can be lighter using less steel. It's an innovative and cost-cutting design that has never been attempted quite like this anywhere in the world. "500 miles to the south in Vicksburg, Mississippi, the design will meet one of its first real tests. The Army Corps of Engineers has built an exact model of the Mississippi where it flows past Alton between the old bridge and the site of the new bridge. Even the tricky currents and eddies are perfectly reproduced. The point is to see how the river, the old bridge, and the new bridge will interact. In their design for the new bridge, the engineers have put one tower, or pier, right at the edge of the shipping channel, and the other pier as close as possible for the shortest and thus cheapest main span.
Okay, this is the original location of the Illinois pier of the Clark Bridge. The Missouri pier location was fixed, and the navigation span was going to be 687 feet.
With the help of a little confetti, the first problem with the Illinois pier was quickly revealed.
As the flow moves downstream, the confetti on the surface actually has to separate and go around the pier itself, and navigation would not want to be around all that turbulence right around that pier.
Too much turbulence might spell disaster for the barges traveling up and down the river. Even worse is the powerful cross current that will try to force the barges into the pier. Together, the turbulence and the current will make it very dangerous to get past both the new and old bridge during construction.
After we evaluated the initial spacing of 687 feet as it was originally designed, we looked at extending the spacing to 850 feet from the Missouri Pier to the Illinois Pier. One of the concerns with this is the longer you make this spacing, the more expensive you make the bridge. Eventually, we looked at different alternatives, and the final resolution we came up with was to move the pier so it lined up with the trail dike that the Corps of Engineers was going to build.
This dike will run from the old bridge to the new to help control the current. Together, the dike and the pier's new location will make the channel safe for the barges passing through it. When all the elements of the bridge are analyzed, tested, and costed out, detailed drawings of each section are made. But for the engineers who have spent 5 years on the project, the ultimate satisfaction is the quiet elegance of the final design.
We design our cable stay bridges to match the environment, not just the span length or the vertical clearance, but where is it going to sit? How is it going to look? And we want it to look like, as best we can, a sculpture, a piece of sculpture if we can do it. It's important to us that the bridge be a symbol of the area. In fact, we look at some of our designs as truly being signature bridges. They're bridges that are focal points of the community.
By the summer, the time of planning is over and the gritty reality of construction is about to begin. The project team will have 3.5 years and $90 million to complete the task. For these construction workers, the job will be as tough as any they've seen. They'll work in all kinds of weather and even put their lives on the line. Their average experience is 15 years. Their average salary is $21 an hour. As for their attitude, it's simply get the job done and get it done right, then move on to the next job. For the general contractors hired by the Illinois Department of Transportation, the pressure will be even more intense. In construction, above all other businesses, time is money. Some of the contractors have even staked their company's future on finishing the job on time. Like Bill Webb, they've all made fixed bids, which means they'll all have to pay for mistakes and delays out of their own pockets.
I've made this statement several times before. It's about one step away from going to Las Vegas and rolling dice. It's a little bit less risky than that, maybe.
Supervising the contractors is Earl Dare, the project manager, or resident engineer for the Illinois Department of Transportation. A farmer-turned-engineer, Dare still lives near the family farm 40 miles downriver from Alton. Dare is as good-natured as they come, but he's also determined to keep the contractors in line.
I don't know if you say if you could say we're distrustful or trustful of contractors, but we do have to watch all the operations and make sure that they're done properly. And that's not to say they were done wrong intentionally. We just want to assure ourselves that all the pieces fall into place in a proper fashion and that all the material is good material.
There's a separate contractor for each section of the bridge. The Illinois Highway approach, the Missouri approach, the cable-stayed main span, and underneath that, the 6 main span foundations. As construction finally begins, Joe Leach oversees the placement of a huge steel frame which will rest on the river bottom. The anchoring of the frame is the first step in the construction of the main span foundations.
We don't necessarily build this thing in a progression from one bank to the other. For example, in this project, we're starting in the middle of the river.
Well, that gal will get right in there.
In starting there, you have to make sure that everything is in alignment so that everything later will attach to it properly so that it will fit.
We'll get enough lines to hold it here to where we can get that other frame on.
The river here is 4,000 feet wide, maybe not quite that far, and we're trying to get everything located to within 1/8 of an inch. The closer you are to, shall we say, perfection, the better the end product.
Now, making sure each frame is aligned perfectly requires precise measurement and constant maneuvering.
Let's get this thing in alignment first, okay?
As the barge with the frame holds position 1/3 of a mile out in the river, a surveyor sets up his equipment on the shore at a geodetic marker. From this fixed point of reference, the surveyor will shoot a laser beam at this mirror mounted on the foundation frame. The frame is in position over the place where one of the foundation piers will be. By measuring the time it takes for the reflected light to return to the shore and the angle at which it travels, the surveyor can calculate the frame's precise position. But the powerful current makes it hard to keep the barge from drifting out of position.
My boat's got me now. I'm going upstream. I'm holding myself down. How are we on alignment now? Hold what you got. Hold yours, Robin. The high side needs to go downstream 210. Illinois needs to go upstream 210. 2 more tenths on the upstream. Little more, Robin. Knock off a little bit, TJ.
When the frame is in the right place, 150-foot-long steel shafts called piles are lowered through the corners.
Just boom him up.
When the pile hits the bottom, it will sink into the mud a few feet. Then it'll be pushed another 60 feet down. When all 4 piles are driven in, the frame will slide into the water. Once the frame is in place, it's enclosed with a tongue-and-groove steel wall. Slowly, step by step, one narrow panel at a time. The finished box is called a cofferdam. Massive steel pilings are driven through the bottom of the cofferdam, through 80 feet of mud and gravel until the pilings hit bedrock. Then 8 feet of concrete is poured in to seal the bottom. With the cofferdam holding back the river, it can now be pumped free of water, enabling the crew to work beneath the surface. The crew's first task is the construction of an elaborate grid of reinforcing steel. The grid will serve as the skeleton for the finished concrete foundation.
Most of the reinforcement for this project was a massive jigsaw puzzle. The importance of this reinforcement all gets back to the fact that we do not allow concrete to take any tension. Now, it'll take a minute amount of tension, but Concrete is, to look at concrete is like a piece of chalk. It's very brittle. And it's very easy to snap. And where it starts to break or snap is where we have to have this reinforcement in there to take that tension.
Each reinforcing bar, each level of the grid has been carefully designed by the engineers for maximum strength. When the reinforcing steel is buried in concrete, the finished foundation, called a footing, will have to carry the weight of hundreds of thousands of tons. It's shortly after dawn on a chilly December morning when the first concrete pour begins. For the next 15 hours, trucks will arrive every 7 minutes. 130 loads of concrete in all. The concrete arrives already prepared. A sample from each load is tested just before it's poured to make sure it has the right consistency. Too much water will weaken it. Too little will create air pockets when it hardens, reducing its strength. After testing all the concrete needed for this footing, about 2,000 tons of it is pumped through a long pipe to the crew in the cofferdam below. The pour cannot be stopped once it begins. It has to be continuous to ensure that the concrete sets properly. "12 feet below these men, the reinforcing is so tightly placed that the concrete won't flow without help from electric vibrators. But it isn't easy to keep your balance on the slippery steel.
Sometimes it's like down in that hole. The guy make the wrong move down there and you'd be singing soprano the rest of your life. So you never know what's going to happen on a construction job, you know. Things be going along good and all at once everything starts going bad.
But today, the work has gone smoothly, and there's nothing more serious than the usual aches and pains.
Pour is essentially complete. We probably got another half hour to go yet. Men have done their jobs well today, and you have to consider they've been here since 7 o'clock this morning, and it's now getting close to 10 o'clock. The same crew has been at it all day. You can imagine their arms and legs are pretty tired.
Oh, there's a job, buddy. That was a day's work.
Finally, after months of the most painstaking effort, the main span foundations rise out of the water within just 1/8 of an inch of their planned positions.
All of these hidden things and that which was built below water are very important. The foundation for this bridge itself is one of the most important things we could have, because that is what holds this whole thing up. If we had piling that weren't driven properly or weren't driven to the right bearing or to rock, we could have a possibility of the whole thing sagging to one side or the other. So these things that can't be seen is what the public puts a good deal of trust in engineers to make sure that the stuff is properly installed.
The next step is the construction of the foundations for the Missouri approach to the bridge. Here, the engineers have had to be unusually innovative because the river is 70 feet deep on the Missouri side, and the pressure at the bottom would crush a conventional cofferdam. Their solution is to build a platform on stilts 40 feet up from the bottom where the water pressure is much less. This platform will then serve as the base of the cofferdam. Next, 24 steel tubes are hammered all the way to bedrock and filled with reinforcing and concrete to become the permanent supports of the Missouri approach foundations. Then the walls of the cofferdam are built panel by panel. The holes in the concrete slab where the tubes go through must now be plugged by hand. The work is handled by a few men taking risks that most would shun. They begin one frigid morning.
It's pretty cold down there. You can make it about an hour before you get real cold. And we'll be taking turns. Me and him be taking turns doing it. He'll probably be in there 45 minutes or so. There's no visibility at all. Well, you just feel around down there.
I have my head on the pipe. Waiting on it.
Drop a little one in there. Here comes the little one. There's a concrete pad down there that is supported by these rebar, and these 30-inch piling are drove through there, and he's sandbagging around the piling so when they pour the seal down there that the concrete doesn't run out around the pipes.
Drop me about 4.
4 big ones?
Yeah.
4 big ones, Tom.
The bags contain sand and cement that, once submerged, will harden into concrete, sealing the holes. Only then can the cofferdam be pumped free of water. But the diver's work isn't over yet. 2 sections of reinforcing steel must still be lowered into each of the tubes before they're filled with concrete. But while the crew is working, several sections break loose in some of the tubes. When the crew fails to fish them up with a hook, they have to send down a diver.
Pull that cage out, then we'll get that other one, okay? The 30-inch pipe, and it's 3 or 4 quarters. You got claustrophobia, you never get down there.
The diver's lifeline is an air hose connected to a compressor. After he descends, he'll feel for the top section of the steel with his feet. When he reaches it, 60 feet down, he'll tie on a lifting line and signal to be hauled up. Ten minutes later, the signal comes. It's an exhausting and dangerous dive, but it's only the beginning. 3 more sections of reinforcing steel will be snared by the diver in this cofferdam alone before the day is done. While construction continues, the river flows inexorably towards winter. If anything, the pace is quickened. Barges and tugs by the dozens pass Alton each day, filled with every conceivable type of commodity. Leviathans of steel dwarfing other vessels, they are piloted by the inheritors of Mark Twain's legacy. Steve Wedding has been a river pilot for 25 years.
I've got soybeans, corn, and wheat. About 21,000 tons overall here, total tonnage. 12 of the loads came out of St. Paul. And then I picked up 2 at Burlington, Iowa, and 1 more near Keokuk, Iowa. Finished me out to 15, which is as much as we need to bring out of here south, and that's all the locks will hold, for that matter, is 15 loaded barges southbound. A lot of these bridges up here on these rivers were built for old-time packet boats, paddle wheelers. They weren't the size of this boat alone, much less 1,000 feet of barges in front of you. I'm 105 feet wide. When you're trying to stick 1,000 feet of this through there with a cross current running through it, it can be very ticklish. My grandfather and his brothers pushed old wooden barges and carried cider out of Calhoun County down here to a vinegar plant in Alton, and they had a small boat and dredge. They dredged to begin with was dredging sand on the Missouri River. Started a fleet over here, and it just grew from there.
The Mississippi has always been a working river, attracting men like Steve Wedding and his ancestors. "2,300 miles long, it's the nation's greatest waterway. But at more than a mile wide in many places, it is also a great divide, splitting the country in two. Until the mid-1800s, there wasn't a single bridge that spanned it. A pioneer family heading west might wait days for a raft to take them across. For years, even the people who lived in the river towns had to rely on ferries. Inevitably, the fast-growing but bridgeless cities on the west side of the river felt cut off from the eastern side and its commerce. Crossing the river became even more important with the coming of the railroad, tying the country together in a fast-growing network of transportation. Finally, in 1856, a new era began, when the first bridge across the Mississippi was built between Rock Island, Illinois, and Davenport, Iowa. But there was trouble almost immediately when a steamer rammed the bridge and sued the railroad. Arguing for the defense was a young lawyer named Abe Lincoln. "A man has as good a right to go across a river as another has to go up or down it," he declared. Lincoln won the case, and bridges have spanned the Mississippi ever since. Although most of the earliest ones have long since disappeared, a few remain, triumphs of design and engineering. These are the ancestors of the new Clark Bridge at Alton. When the main span foundations are finished, it's time to build the towers on top of them, section by section, until they rise 300 feet above the water.
Realistically, a half-yard block of concrete is going to be plenty, ain't it?
McCarthy Brothers Construction of St. Louis has less than a year to finish the towers. Ted Downey is the project manager.
You know, just ferry them in back and forth. Working over water is one of the toughest things you can do. You have to plan every morning, which we do. We meet every morning with the staff for just a few minutes because you can't just walk out and take something or drive out and get somebody. Everything has to be maneuvered by tugboats and barges.
At 7 in the morning, a McCarthy crew of about 30 is taken by boat to the site. Already, the dike has been extended to the Illinois main span foundation by the Army Corps of Engineers. Today's job is to add more reinforcing steel to the foundation as the tower grows. This wire will hold the horizontal reinforcing bars in place until concrete is poured. But the vertical reinforcing will get special treatment because it must carry more weight. It needs a connection as strong as the steel itself. So on the end of each vertical bar, there's a steel cylinder or sleeve guided over the end of a ridged bar already embedded in the foundation. Then a splice is made by a special tool called a swager. It squeezes the sleeve so tightly that both ends of the bar are joined together in a permanent bond.
Hey, Dave?
Yeah.
Do a favor for me, sir, while you're there?
I guess I owe you one, don't I?
Yeah. Can you check the elevation?
After 3 months, the first sections of reinforcing steel are covered by concrete. The towers are now 70 feet above the water. But in the late fall here, the weather often takes a turn for the worse. A rising wind is the harbinger of winter. Just as the steel forms for the next concrete pour are hoisted by crane, the wind decides to gust.
Lately, our luck's been running pretty sour, to be honest with you. In behind us here, that farm above on 10, we had problems with that. We attempted to set that farm 3 times and had to set it back down.
You can't control the load. It's out of control. The wind controls it. In other words, you don't control it.
Yeah, if the farm would happen to spin, like I said before, and got hung up in this boom, that could be bad. You could lose the boom. Or it could knock somebody off, off the column. Or it could damage the existing concrete, the re-steel, or even a farm if it got away from us. But those are some of the hazards of setting, these big farms like this in these high winds. They're talking about 30 to 35 mile-an-hour gusts.
Today?
Yep. And what you see is what we're gonna get for the rest of the day. It's not gonna let up any. You don't think we could just get up there tight to it and ease it up and slip it down over the re-steel?
Talking about, it'll catch a lot of wind. Okay.
So your gut feeling is?
I'd rather not.
Better not do it.
That afternoon, rain arrives on the heels of the wind. But on the ground, work continues on a new section of reinforcing steel. When it's finished, it will be lifted to the top of the tower in one piece. The iron workers have special guides or jigs on the deck to make sure they assemble the bars in the right pattern.
The reason for all this intricate layout work is that this tower tapers ever so slightly from elevation, say 500, all the way up to 630. And in order to make this gradual decreasing size, each one of these bands has to be moved 1/4 of an inch in one direction and 1/8 of an inch out in the other direction. So each band that we make has to be individually laid out, which is very unusual for reinforcing steel work.
There are nearly 4 miles of steel in this section. It weighs 45 tons. The section is so heavy, a warning siren goes off on the tower crane, which can't bear the weight alone. Once in the air, it can only be handled by another, more powerful crane on a barge. crew must now match up each splice with its mate.
Got mine. Okay, so what's it? Hold on. Just touch me.
Don't Mark need his ass in here on this wall.
It will take a day and a half to finish the job. From now on, the towers will grow in these 40-foot increments. And the efficiency and safety of it all depends heavily on one of the most isolated men on the job, the tower crane operator. He can make the difference between profit and loss.
I detest heights, but up there, I'm inside of a cab. It doesn't bother me when I'm high. But it really doesn't bother me. Just take a beam this size and put that thing 10 feet off the ground, I couldn't walk it. But something like that, if I'm inside of something, it's like a safety factor for me. It's the way I am, it's the way I've been all my life. I never always will be. Just getting up there, it gets you awful winded. It's a long climb. That's my home for 9 or 10 hours a day up there. On a clear day, I can probably see 20 miles. When I get here, they go to work.
Touch her up easy, Bruce. Hold that, Bruce. Just a touchdown. Hold that. What are you reading? 20,100. All right. Bring her down to about 12. I'm ahead of it about 2.5 feet now, Dave. It'll blow on the wind down here, Tim. It'll be a straight wind. It'll be a lot easier to control it that way.
Once the steel forms are in place, the next concrete pour can begin. At first, everything seems to be normal. There's only one problem. The concrete the crew just poured has failed the Earl Dare strength test.
I took a hammer and chipped some of the concrete off the surface, and I noticed that it was very soft. It was very lightweight. I took a sample down with me to the field office, and I noticed it was so lightweight it would actually float on the water.
When you're stuck with over 600 cubic feet of bad concrete, your options are extremely limited. In fact, you have only one. Get rid of it, and fast.
We're in the process now of taking it down to a certain elevation that the state said where it's good concrete. Probably, as you know, it throws us way off. The blinking shuts, basically the whole job down before it's pouring.
No one likes to hang around because of a supplier's mistake, especially when you're losing money. With the bad concrete, there's a greater temptation to make up for lost time by speeding up the work and taking more risks.
There's a danger to, yes, if you get too involved with the bridge, I mean, if it becomes your sole thought in life, you begin to forget about the human beings that are actually building it. And that's something that in the building of these things you can never do.
It's pretty dangerous work for these guys. It's very dangerous work, as a matter of fact. We're extra careful out there. We put a life belt on anything that moves, and that's just the way it is. It's the nature of the beast.
Every construction worker knows someone in the trade who was in the wrong place at the wrong time.
We had a friend of ours just killed a couple weeks ago, you know. Accident, some unforeseen thing. Hooked onto a load, and evidently he was under it or in the path of it, and some kind of way he worked out of the chokers and fell on it, you know, broke, you know, a number of bones in his body, and a couple weeks after he died. So most of the guys out here are real safety conscious. The company is safety conscious itself. We don't want to see nobody get hurt.
To be safety conscious is not always enough, though, as each worker knows. Consider the case of Tim Summers, a carpenter who owes his life to a stroke of luck. Some would call it a miracle.
If you got a picture of those tower cranes that's on there, he basically fell maybe 100 foot. It was quite a fall. Just lucky he didn't, you know, didn't get killed. That's, you know.
I don't know how to swim, so this life vest is the only thing that did it for me. She bolt gave on the scaffolding, and I fell about 75, 80 feet. I hit my head on something on the way down. I'm not quite sure what it was. Hit the water. I missed the barge by 12, 15 feet, I guess. That was where I lucked out. And I just popped up. Just came right out of the water and grabbed onto the ladder. It was right there. Climbed right out.
Like nothing ever happened.
Well, no. It was like something happened. I just happened to luck out and not hit the barge, and the ladder was there. Otherwise, I'd have been right underneath the barge.
Kind of stoic understatement rules here. But it doesn't take outsiders long to figure out just how dangerous this job really is. All you have to do is look around. Just watch as two ironworkers finish off the latest section of reinforcing steel, 250 feet above the water.
I see him coming in. I see him coming in. So high, Dick. 6 inches, not 6 feet.
Is that the speed you want?
Yeah, you're doing fine. Just keep on coming down. Hey, Tommy, put the safety belt on and hook off. Hang on, man. I'm gonna have a finger from this. Hey, this is late, son.
Oh, I didn't see you.
You're getting me nervous.
Keep them apart, babe.
All the time.
There too.
There are too many of them knuckle busters. John, when you hook up these next ones, take them all the way up to the bend in the hook.
So far, no one's been seriously injured on the job. Then again, there are still 20 months to go. It's now February 10th.
Don't mess with me, Tim. Come on down, Nancy. Good. Don't mess with me, Tim.
A typical 8-hour shift begins at 7 a.m. Most of the workers live within 15 miles of the site, but some had to travel more than an hour to get here.
We're gonna go out and attack the sub-zero weather.
Yeah, it's
Wind
minus
chill.
2. If they pull them farms, you know what that's gonna be like.
Hang on, baby, and hope you don't go for
turn them loose.
What say, Bo? You ready, baby?
Ready to go home?
Today it's cold and raw,
Hi, honey.
Hi.
but the camaraderie of the crew is, if anything, stronger.
That's not been damn near had me in the river.
See that wallpaper Steve boy hat?
Oh, that's awful.
Good. All right, good work.
If you're a construction worker, you have to show up no matter how miserable the weather, because you won't get paid unless you do.
My adopted dad here.
Workers pride themselves on their toughness. But winter on the river is especially hard. The sky promises more snow. An hour later, it begins to fall, lightly. Then more heavily.
It's good weather, get frostbite and stuff, you know, just no need to take a chance. A little unbearable up there this morning. The wind's blowing about 25, 30 miles an hour, about 0. When you got to depend on climbing around and your fingers getting cold and stuff, it's just too dangerous for me up there. I don't feel comfortable. few of the carpenters, we had that weather sock blew off the top. We got it pulled down, but I think they're all going to come down too before long, and they get a little taste of it up there. They just come up after we did. Can't keep a hard hat on. Your hard hat blew off. Like I said, I just think it's too dangerous up there this morning.
There will be more snow throughout the winter. It's a constant struggle to keep from falling behind. Despite the weather, the two towers are nearly finished by the spring. Within a few days, one crew puts in the first steel girders that will support the road deck. At the same time, another crew is getting ready for the final stage in the tower's construction. This curved saddle-like structure will crown each tower and hold the bridge's cables. It goes up in two pieces, which must be joined at the top.
Straight up easy. Going up. Going up a little bit.
Later, this space beneath will be filled with concrete, permanently supporting the plates and the cables that will drape over them. And so for the last time, buckets of concrete are sent to the top of the towers. When the concrete is set, the steel forms are removed. The towers are finished at last. The end of a long struggle against time. The towers aren't the only part of the project, however. On the Illinois shore, another contractor must build the approach leading to the bridge, and he's already running late. Things quickly go from bad to worse. An accident stops construction in its tracks only a few weeks after it begins. A crane is tipped over while trying to lift an oversized load. Worse, the operator may be hurt, although how badly isn't known yet. He'll be taken to the nearest hospital for tests. This is the moment that everyone dreads, the possibility of a serious injury. Fortunately, the man will recover, but the same can't be said for the schedule. There are further delays when dredging begins for the underwater foundations. Something is down there that the crew didn't expect.
We couldn't complete the excavation because we hit something and couldn't get through it, around it, or under it. So we sent a diver down to take a look at what we had, and that's when we found out we had a barge. And they're chopping through the inner bottom right now, and it could be up to 200 feet long. And all we need is a section big enough out to get our pier in right here.
We can't do any work here on pier number 13 until this is resolved. And one of our cofferdams is directly over this sunken barge. So until that barge is removed, we can't go to work on pier number 13. Number 13, that's a lucky number, isn't it?
Our costs to keep a job like this going are, maybe in the neighborhood of $100,000 a month. So if you lose a month on a job like this, you never recuperate all of that. That's part of the risk of doing business.
With this huge square of rusty steel removed, the crew can finally go ahead with pier number 13. But the river yields to the bridge only with the greatest reluctance.
Even though at the present time things look relatively calm with the river, we know that it can give us problems, and it tends to be rather unforgiving. Some writers have even referred to it as a great brown god, and I think that's one of the things that some of us anyway, those of us who have worked on the river before, certainly have a healthy respect and will always attempt to maintain a healthy respect.
But respect may not be enough in the months to come, when even the bridge itself will be threatened by the river's might. It's now 2 years after construction began, and the most challenging and nerve-wracking phase lies ahead. For the next 16 months, the crew will have to wrestle with untested techniques, costly mistakes, and even the river itself. By the summer, the main span towers are finished, and the crew's getting ready to install the first cable stays, which will support the road deck. Each cable stay will run from one side of the deck over the top of a tower and then down to the other side. A stay consists of from 19 to 46 steel cables housed in a protective steel tube called a banana pipe, named for its color, and a flexible black plastic pipe for weatherproofing. At the ends are anchorage devices to help fasten the stay to the deck. The cable for the stays is made in Jacksonville, Florida. There are about 112 miles of it, wound in spools. Specialized machines spin the cable out of 7 strands of high-strength steel. To resist corrosion, the cable is then coated with epoxy. It's also covered with white grit. The grit will keep the cables from slipping once they're bound together. The last stage is the waterproofing test. Crucial, because even minute spots of corrosion on the steel can lead to a devastating failure. Another potential problem is the enormous length of the cables, because they're designed to drape over the top of the tower in a continuous strand. As it turns out, the extra long stays quickly make for a construction nightmare.
Initially, we were pulling the cables through the banana pipe up there, 1 and 2 at a time. By the time we got 37 cables pulled through, why, a good deal of the cables were unusable in the pack.
This was a method he had chose to use, and we thought it's up to him to give it a try. And after he had done that, we took it apart and looked at it, and this is what we found. One cable was actually rubbing over the top of another cable. As you can see here, it took off some of the epoxy coating, which we don't want. This coating that's on the cable stays is very abrasive, and as one cable was pulled across the other, it actually cut into the cross-sectional area of the steel itself, which would detract from the strength of the cable.
A month and a half has been wasted, along with thousands of feet of cable. There's no other choice but to start over from scratch.
Now we have developed a system of pulling the cables out individually and then putting them all together and pulling all of them together through the banana pipe. So they only make one trip through the banana pipe and they don't wear on each other. And it looks like this is going to be the way we're going to travel here. The longest ones are like 768 feet long. Right now you're seeing cables that are only 400. As we get into more cables and longer cables, we don't know if our equipment can pull them.
Want to get it up further, Ed?
My gosh, we're going to be down the road a couple of blocks stringing the cables out. It's just going to present a whole new set of problems for us. But like here, why, we'll just kind of have to work our way through them. Nobody had ever done this before anywhere in the world, pre-assemble these cables like this. So what we're doing here is we're cutting new ground.
The next objective after the cable stays are built up is to take a configuration of cables like this and thread them through something called a wedge plate. And a wedge plate is the device that enables us to anchor the cable stays to the structural steel of the bridge, and that's what will ultimately hold the bridge in place.
That's number 22.
It's kind of like threading 46 needles at one time. We're trying to line up 46 individual holes and thread all 46 of these through at one time.
All that.
The alignment of the individual cables as they pass through the wedge plate is critical. We want the cable to be perfectly perpendicular to the surface of the wedge plate. We also want the cable to be centered in its hole. The weight of the structure is carried by the cables. That load is transferred from the cable to the anchor assembly by these little jaw devices, which are called wedges. And they do this by small teeth that are cut into the wedges. These teeth bite through the epoxy coating into the steel of the strand itself. They're small, but they're mighty.
I straightened this one up.
All right, these wedges here have to be equally spaced around the cables to ensure proper fitting when they stress the cable out on the bridge. If you get two of them to one side, you cause a big gap over here, they'll bite the cable incorrectly and could actually kink it or cut it. Then you wouldn't have the strength on that cable. So each individual wedge gets special treatment. You know, we look at each and every one of them and make sure that they are set right.
If the problem of assembling the stays has been solved, that still leaves another, getting them up on the tower.
Over.
The solution here is to move very, very slowly, both on the ground and in the air. It takes 3 cranes to lift the stay, 1 for the banana pipe in the center and 2 for the ends. When the banana pipe is just above its bed, the crew begins to move it into position. Each stay has to fit perfectly into an anchorage slot. There's only a fraction of an inch to spare. When the stay is finally secured on top of the tower, other workers at the bottom turn their attention to each end. This is what knits the bridge together. To pull the stays tight, special jacks called rams are then brought in. It costs $1,300 a month to rent just one. But they're the only tools that can do the job. Every time the cables are tightened, it takes 4 rams. The cables have to be stressed in pairs, 1 ram on both ends of each cable. First, the end of the stay is inserted into a guide pipe. Then each ram is installed far below the top of the tower at the stay's anchorage point. The cable is fed through. The ram grips it and pulls it tight, 12 inches at a time.
On 5.
As the ram tightens the cable, the amount of tension is carefully monitored.
7.
Each stay is tensioned to a carefully calculated degree, tight enough to support the deck and loose enough to flex in the wind. When another summer has passed and autumn is painting the riverbanks orange, the surrounding countryside waits expectantly for the bridge and another harvest. Autumn is the time of reckoning for every farmer. Here, the grain is golden in more ways than one. It's the coin of the realm. But even a fine harvest won't bring financial security to local towns. Too few people work on farms these days, and too many farmers are in debt. Instead, the hope of a place like Alton is to become a more prosperous suburb of St. Louis, a bedroom community with charm. A fine place to raise children, dogs, and property values. And to keep the cash flowing, a prime tourist attraction as well, with reminders of Mark Twain's America, when Alton was at the pinnacle of its fame and fortune. But to make Alton great again will take more than echoes of the past. Alton needs a modern bridge for a modern age, and everyone knows it. The bridge is big news, even at Alton's Eunice Smith Elementary School. Today, a class is taking a field trip to see for themselves. A model of the bridge has been set up on the banks of the river, overlooking the site.
Don't take it up piece by big piece.
Good morning, everybody.
Morning.
What we're trying to do here is build a brand new bridge to replace that old bridge you see in the background here. You all know how narrow that is and how bumpy it is. This is what the new bridge is going to look like where it crosses the middle of the river. Now there's more of the bridge on either end of it that's not shown, but this will be the main part, and it'll be 4 lanes wide, so it'll carry at least twice as much traffic as that bridge. And it'll also have a bicycle lane, so you can ride your bicycles back and forth across it. It's going to be kind of neat to ride over the river in your bicycle. Yes, ma'am?
Will we have to pay higher taxes?
No, you will not have to pay higher taxes to drive this bridge. Where the money comes from this bridge is every time your mother and father buys gasoline at the filling station, they pay a little bit of tax on every gallon. And right now, I believe in Illinois, it's about 16 cents per gallon of whatever you pay goes into a fund to build bridges and roads. And that's how all our bridges and roads are paid for in the whole country. It comes from taxes on gasoline. You in the back here in the black shirt.
How much will it cost?
How much will it cost? We think it'll cost right at $90 million. Yes, sir.
How many cables will it take?
Back in the classroom, the children design their own bridges.
Okay. We gotta scoot this back on.
The moment of truth comes a week later,
You guys back a little
when
bit.
each model is put to the test. The winner will be the one that can bear the most weight.
No bridge will probably make it out alive today. Maybe some of them will. They may hold all of the concrete blocks. The giant blocks, the big concrete blocks, weigh 55 pounds each. 55, okay, wait a minute. The small ones are 38 pounds each. Rania, you will be first. Come on up. Bring your bridge up. Okay.
From the start, the kids get a vivid lesson in the science and art of engineering.
It held 38 pounds. Comes the second one.
76. Yes.
Okay, 76. Okay, go right ahead with the next one.
This is weird.
Rania, come on over where you can see it, hon. Okay.
Rania, why don't you come and
over here.
sit down so that it's not dangerous, but sit down.
The kids also witness firsthand the cruelty of gravity. And the winner? A model holding more than 100 times its weight. At least for a few moments.
Definitely held three. Definitely held three.
But it's the power and beauty of a well-designed bridge that fittingly ends the lesson.
Big, Bright Bridges, poem by Marlon Lancaster. Big, bright bridges, radical, waving river, interesting, rocky roads, enormous, skinny spans, dangerous bike routes, great, beautiful bridges.
When the first cable stays and structural steel are in place, it's time to install steel girders for the road deck. 300 miles away in Des Moines, the fabrication of the girders takes place at a company called Pittsburgh Des Moines. The process begins with a plate of raw steel. This plate is destined to become an edge girder, one of 66 in all. When it's finished, the girder will run along the outside edge of the road deck. To make each one takes 3 immense pieces of raw steel. They're all custom made. They're measured, cut, welded, drilled for bolt holes, sanded smooth, and swept clean. The company can assemble 3 of them a day at a cost of $30,000 each. 35 feet by 5 feet, the finished girder weighs about 17 tons. It will take 6 months to fabricate all the structural steel for the bridge's main span. Today, one of the first pieces is beginning the 18-hour trip to Alton at the dazzling speed of 20 miles an hour. Back at the site, all the pieces must fit together perfectly. This section of the road deck arrives in 4 main pieces, which are joined together on the shore.
Come down a little more.
After it's assembled, the 100-foot section is hoisted up by a pair of cranes. And this is where it's headed, to a prime position close to the tower. The 2 crane operators must be enormously skilled, one at each end of 76 tons of steel dangling in midair.
Coming up. Coming up.
Hold that, hold that. Come on. Oscar, we're in. Come on.
To line up the bolt holes, workers hammer in steel spikes called drift pins. Then the bolts go in, at first fastened loosely by hand, then tightened later for optimal strength.
In the newer steel bridges, they're going to lighter weights and stronger steels. Under the old bridges, they were so overly designed that it really didn't, make any difference. You could have a few loose bolts, and the bridge would still be safe. But under these new systems, it is imperative that the bolts be properly tightened. This apparatus has a double socket, one on the inside that goes over the tip of the bolt, and on the outside which goes over the nut, and they turn in opposing directions. The nut will be doing the most of the turning, and when it reaches the proper tension, the inside socket will twist the tip of the bolt off. When this tip is twisted off, you know that the bolt has been tensioned properly.
This is when the bolts face the greatest amount of stress. Since each section of deck must be installed before its cable stays can be attached, the bolts alone must carry the load for now. But they won't be asked to work alone for very long. Within a day, more cable stays will go up. And then the deck will be ready to carry its own burden. These massive concrete slabs will become the roadbed for the bridge's main span. And so the process is repeated. As the structural steel pushes outward, the stays follow close behind, supporting the weight from above. Each cycle is supposed to take 2 weeks. But goals are one thing, reality is another. In construction, you tend to get nervous when everything goes too well. You just know that something is bound to go wrong. This week's problem is a potential disaster. Even Earl Dare is becoming a bit grim.
The results of our first cable stay test just came in, and this was a full-scale mock-up of an actual cable stay. The results were not encouraging at all. We experienced a number of wire breaks. We experienced some corrosion. We know we've got some serious problems. I don't know if we'll ever be 100% certain, but all fingers point toward corrosion in the strand as it was being manufactured.
We've got a problem if it fails again, and that it will delay the material's arrival to the job site. We cannot install any materials until these tests have passed.
The crew is running out of approved cable. And after that's used up, all work on the main span may have to stop. Further tests are ordered, but they'll take a month. For the management team, it's the longest month of the project. This machine has been tugging at a section of cable stay every 2 seconds for 30 days now, simulating 50 years of wear and tear. The process is similar to taking a piece of wire and bending it back and forth until finally it breaks. The sample stay has already been stretched close to the breaking point. If it pulls apart now, it too will be rejected. A failure here will cause even further delays and cost millions. The test is so critical to the project's future that representatives from the design engineers, the Illinois Department of Transportation, and the contractors are all here, waiting anxiously.
1 1/4 inch has moved since we started at 300,000 pounds.
We just run it now for the duration?
We just go through it now.
It's got to be close.
946,000 pounds is the target load. But instead of a blood-chilling snap, There's only a deep sigh of relief. The sample has passed the test. When the stay is sliced apart for closer examination, everything is intact. Further tests of other samples will go just as well. The crisis is over. There will be other crises, both large and small. The tightening of the cable stays has been plagued with problems.
A little more down. Hold that. What? Well, right now we're taking the slack out of the cable. And I'm running the ram back in now to get another bite so I can pull some more out. And it'll pull it in 12-inch strokes.
Going on up here. And check the top, it's clear. You know, it sounds like it's going on inside the wedge head there.
We better take a look at it. The cable on the other side is just hearing some popping noises, so we're going to check into it. All we're trying to do is prevent any damage at all to the cables. Anytime it does happen, we have to fix it. Otherwise, it won't accept it as is. You know, it has to be right. 2 strands are scraping again. I've got 1 wedge that's popped out. Same problem as usual.
A recurring problem that we had last time.
If one of the cables has slipped and is not gripping properly, all of a sudden the loads are transferred to the other 45 cables, and that's not what the designers intended. Sometimes we find that these cables have evidently slipped somewhat, and what the crew has found out there is that some excess epoxy has built up inside the wedges. This prevents the teeth from gripping through the epoxy on the strand into the steel of the strand. The immediate remedy is to replace them with wedges that have good clean teeth that will again bite through the epoxy and into the steel of the cable. This is a very expensive operation for the contractor, and it could take him up to a day to remedy just one slipped strand.
Bring my screwdriver and my client.
It costs almost $1,000 an hour in wages, equipment, and overhead just to get a new wedge on and rethread the cables. Later, on the other side of the deck, there's another problem which has the crew mystified. The cables have gotten stuck in the ram. But this time, the culprit isn't a wedge. Once again, the ends may have to be cut and rethreaded.
If we can get another 5 inches of pull, we can expose the whole thing. And get to the bottom of it, maybe.
That's what I like to do.
Well, it's a piece of the same plastic that's this spacer that is up here. I imagine the piece might have broke off, or might even got placed in there on purpose by someone in the cable yard to hold it in place. I don't know. But it definitely doesn't belong where it's at.
Foreign object. Probably from
Ain't moving at all?
Somewhere. Foreign. Here it comes, baby. Yeah. Piece of wire tie.
It's a piece of a plastic tie that they used to put around these strands. It got down in between. I think that caused our whole problem.
49-cent piece, buddy. Screwing up $1,000 worth of cables.
It's now January, and the crew has shifted its attention back to the top of the tower, where the wind is making its presence felt. It's dangerous enough for the crew 300 feet in the air, but how about the bridge? The elements sometimes seem to toy with it, shaking it at will.
Anyone can build a bridge that will carry a given loading. But if you look at it the way some of those of us in construction look at it, it takes real craftsmen to build a bridge that will just barely carry it.
The bridge is now at its most vulnerable stage. Its 600-foot cantilevers are like kites in the wind.
There are different theories as far as how much wind the bridge can withstand. You have cable that can freely move across the pylon head. The strand actually flows through the pipe, and if you get an out-of-balance force, the strand could slip through the pipe, causing the whole bridge to rock. It'd be very disastrous. Something we don't even want to think about.
No one will really sleep well at night until the gaps in the bridge are closed. The first gap between the Missouri approach and the main span is 35 feet wide. One down, one to go. The second gap is in the middle of the main span. When it's filled, the structure will truly become a bridge. After 2 years of work, a crew of 40 prepares to join both halves of the bridge together. But will they fit perfectly when the last piece is added?
The diagonal temporary struts down.
A surveyor has been checking the position of the two ends since 4:30 a.m.
Hey, Jimmy, let's do this side. It can move up to 2 inches this time of the year. Right there will be fine. In the summertime, when the heat, radiation from the sun gets on, it may move 3 or 4 inches easily. That's up and down. It also moves from side to side until it gets connected there, because it's like it's two separate entities right now that can swing back and forth. The bridge this morning is in good shape. Last week, we adjusted all the cables on that pylon over there. And this week, we've been adjusting these. And now we have to make sure at a certain temperature that they're at the exact same elevation. We also have been monitoring the distance in between, because they had to cut that piece special to fit there. And it's cut to be fit at 68 degrees. That's the mean temperature. But right now it's 68. So it's almost perfect to set it.
The crew is in a race with the sun to get the last piece into place before it or the bridge heats up and expands.
Okay, pawl boom down easy.
When the girder is finally in position beneath the gap, the cranes bring it up slowly. Much to everyone's relief, the girder fits in place. But the bolt holes will have to be lined up in time before the steel expands. Even a couple of degrees difference could make it impossible. At 12 noon, success at last.
shut up.
Now, for the first time, the bridge is whole, spanning the river from Illinois to Missouri, just a few miles from where Lewis and Clark once crossed. When the last concrete panels go in, Earl Dare can't resist a small boast.
No construction project is problem-free, but one thing about this structure, for the size of it and for the dollar cost, which is right at $85 million, there haven't been any major problems that we couldn't solve. My boss, Dale Clore, the district engineer, he said this could well be the first bridge built across the Mississippi on budget and on time.
Little does Earl Dare know that the river is listening. In June, storm clouds gather over the bridge. The rain begins and doesn't stop. The river runs faster and faster, fueled by the storms that sweep in from the west. Only 2 miles from the bridge, the river rises 15 feet. People are used to floods here, but this is a deluge. There's a growing sense of helplessness. The neighboring town of Grafton is overcome. Downriver in Alton, a new levee is hastily built. Sandbags are filled by hundreds of volunteers, adults and children alike, day and night. The levee is set back about 200 yards from the riverbank. It's Alton's version of the Maginot Line, the last barrier against the rising waters. By the middle of July, it's 8 feet high and 1,000 feet long. Everything on the riverside of the levee is given up for lost. The river is so high now, the Missouri approach is in danger. Its construction site is already underwater. It can only be reached by boat.
Back behind me, you can see what was, or I guess still is, our office. The walls are buckled inside the trailer, and the water is up over the shelves in there, and it's getting in the furniture. The file cabinets and the desks will be full of soot and sewage and everything that's in the water. So snakes, rats, all those good things.
Getting a few parts out of the supply trailer requires a major effort.
Come in, Andy.
Yeah, Stevie.
Have you got all the hardware and everything out of there for the drain?
Yeah, all the drain hardware is up above. You don't need anything else, huh? Are you okay?
No, I gotta get you more.
That's all I know, man. It's just a little motor ain't coming.
Okay.
Ironically, the old bridge is now the only one open for 20 miles to the south and 70 miles to the north. In a desperate effort to keep it open, the roadbed is raised by several feet. Truckloads of gravel are rushed to the site.
One-way traffic!
Long maligned as a bottleneck, the old bridge has become Alton's savior. But the news grows worse each day. The The flood is being called the worst in 500 years. Thousands of houses are lost. Property damage is in the billions. From Minnesota to Kentucky, 800 miles of devastation. More than 50 people will lose their lives. Everyone who can heads for higher ground, but the river is right behind them. In Alton, all the valiant efforts are in vain. Water pours through underground utility tunnels and floods the streets behind the levee. Like the original Maginot Line, it is outflanked with ease. Downtown Alton is a disaster, and so is the construction schedule for the bridge.
Well, we're sitting on the approach to the Missouri approach to the Clark Bridge, and as you can see, everything's flooded. Both the Highway 67, which was our access to the job site, as well as the new Highway 67, which is yet to be built. Both are flooded, so we have absolutely no access to the project. The impact on us has been substantial. No work is going on, yet our overhead continues to go on. From a more humanistic standpoint, the flood has put some 60 or 70 people out of work. So needless to say, that hurts.
The main span is also a mess. The crew can hardly do any work, and there is an eerie stillness at the site. They are so close to finishing, and yet time is running out. If they can't finish before winter, they could be shut down until spring. It's not until mid-September that the waters finally recede. Alton will be cleaning up for months. The losses in business and property are immense. And as the town ponders its economic future, the completion of the bridge takes on even greater urgency. In mid-September, construction resumes on the Illinois approach at maximum speed. The crew works 16-hour days, getting the road deck ready for its final coat of concrete. They begin before dawn on the day of the pour. The concrete they'll be laying down is a special type that can't be used if its temperature rises above 90 degrees. But at dawn, the forecast calls for an unseasonably hot day. Hot enough to ruin the pour. And if that weren't enough, there's trouble on the old bridge, which the concrete trucks have to cross. A distraught former mental patient is threatening to jump. Traffic is backed up for miles while the police talk him down. The concrete trucks are hopelessly stuck. Their loads are ruined. The pour will have to be canceled. The next morning, the crew tries again. But the temperature threatens to be even higher. The first load of concrete arrives at 4 a.m. In the early morning, the flow of work is smooth and steady. But by the afternoon, the crew is feeling the strain.
Air temperature is getting close to 95 degrees right now, and they're starting to show some wear and tear. We've got about 250 feet of concrete out on the deck so far. About noon, we were a little concerned our concrete temperatures were getting kind of high. They were approaching 90 degrees, which is our limit. However, the concrete plant added some more ice, and we're able to get the mix temperature down considerably. So we're going to continue pouring till about 3 o'clock this afternoon.
We'll figure it out first, man. We'll figure out what we're going to do. Heater on fire. Look like a raccoon when I go home. It's going to be hot or cold? I'd rather be cold.
Most of these fellows got out of bed about 3 in the morning. They were on the job anywhere from 4 to 5 this morning. We've been pouring concrete since 6, and about 3 o'clock they'll all be beat.
Everyone is feeling the pressure. The contractors could face a penalty of $4,000 a day if they don't finish by December 21st.
The foreman, the various superintendents, they're here around 6 in the morning, sometimes even as early as 4 o'clock in the morning. It's some very, very long days. We had originally figured that we should be totally completed with this job, everything, this past summer. But you don't expect a 500-year flood. There's no way of anticipating that. You don't expect a year with twice or more than twice the normal rainfall. We didn't expect sunken barges. There's several things we didn't expect. And you don't make up for it. A job that was intended to be a normal business venture with an appropriate amount of profit turns out to be, at best, a non-profit operation.
I guess you could say it starts to make an old man out of you. There are days when I feel like that this would. I'm not so sure I'd want to try this again.
There are just 2.5 months to go now. 1.5 months. 1 month. Only a small crew is left, working 12, 16 hours a day in bitter cold. Finally, on January 4th, after nearly 4 years of construction, the crew takes one last walk across the bridge. And now it's Alton's turn.
We are in a brand new structure here that nobody's really crossed over yet, but that will officially take place at 3 o'clock in the afternoon.
And we're broadcasting from the Clark Bridge, right in the middle of the Clark Bridge, as a matter of fact. It's a nippy morning, but
we'll be hanging out at the bottom of this bridge.
Brand new bridge, and what it means to us today is the same thing it meant 68 years ago when the old bridge was built.
For the town, it's a combination of Christmas and the 4th of July in 10-degree weather.
If anybody knows the other bridge, it's kind of breaking apart, and I think it's time for it to rest and this one to start anew.
The other one was really bad. A lot of curves, very narrow. Now maybe Alton will grow. It's beautiful. I've never seen a cable bridge or been up close to one. I can't imagine how they got these giant cables through the top up there like they did. I would have liked to have been here to see that.
Not very often do you see a bridge being open. We wanted to see it up close, get some pictures, get our own little part of history.
We're kind of brave and kind of foolish, I guess. But I wanted her, she was born this year, so I wanted her to remember that the bridge was built on the same year.
Today, each of you mark your place in history by being here for the dedication of the new Clark Bridge. Thanks for coming.
Even with bridges, the cycle of life and death asserts itself. As much as the people of Alton complained about the old Clark Bridge, they need to say goodbye before it's gone.
I do remember it was in the year when the Model A come out, because my dad had just got a new 28 Ford, and he said he was going to try it over the bridge. So that was in 1928.
And now, once again, there is only one bridge across the river at Alton. But even the men and women who gave so much of themselves to build it know it cannot last forever.
We'd like to think that the people following us think, my gosh, they really did know what they were doing. We'd also like to think that our grandchildren, perhaps our great-grandchildren, spend a good deal of time swearing at us when they come back to replace this and try to tear it down. Everything that's built comes down eventually.
But until the day the bridge is replaced, many years from now, it will stand as a monument to the people who built it and a witness to the river's never-ending journey.
How would you span a freeway, a canyon, a canal? At Nova's website, match the right bridge to the right site. Make it or break it at www.pbs.org. To order this show for $19.95 plus shipping and handling, call 1-800-255-9424. And to learn more about how science can solve the mysteries of our world, ask about our many other NOVA videos. Next time on NOVA, beneath the Mediterranean, history beckons. Divers search for the ancient lighthouse of Alexandria and discover more than they bargained for.
It's very beautiful.
Treasures of the sunken city. NOVA is a production of WGBH Boston. Major funding for NOVA is provided by the Park Foundation, dedicated to education and quality television, and by the Corporation for Public Broadcasting and viewers like you.
This is PBS.